All right, good morning, Townview. Let's go ahead and get started. So today we're going to be talking about acids and bases. So go ahead, grab your journals, please. And then at the top of the page, we're going to write acids and bases. That's the name of this chapter. So first, I want to start with what you guys already know about acids and bases because we spent all last week talking about them. So taste bitter, is that an acid or a base? All right, taste bitter. Are you sure? All right, so I'll put acid. I don't know if you're right. Has a pH that's less than 7. What is that?
That's an acid.
pH less than 7, that's an acid. Taste sour, what's that?
Acid.
All right, so acids taste sour and bitter?
Oh yeah, put the base on the first one.
All right, so taste bitter, that's a base now?
Yeah.
All right, feels slippery, what is that?
I don't know.
Acid or base?
Base.
Base. Dissociates in water, acid or base?
Base. No, it's acid. No?
It's acids and base, so this one's both. Known as alkali, what's that?
Oh, base.
Has a pH greater than 7.
Base.
Is neutral.
Just water?
So this one's going to be neither.
Universal solvent.
All right, let's go ahead and move on. So y'all don't need to write any of this. This was just a warm up. So let's go ahead and move on. All right, so let's go ahead and talk about the properties of an acid. So properties of an acid, first one you need to write is that they taste sour. So you already know this because we already did this last week. We're just reviewing again. So properties of an acid, first one is going to be that it tastes sour. Another one is that it turns blue litmus paper red. So acids, they turn litmus paper red. Next, acids, they act as electrolytes, which means when you put an acid in water, it's going to dissociate. Example is going to be HCl. If we put HCl in water, it's going to dissociate to create H plus and Cl minus. So this dissociation leads to it being an electrolyte. That means it conducts electricity. All right, so next up, acids, they have a pH that's less than 7. Acids are also corrosive, which means they cause metals to react. So the fact that they're corrosive and they react with metals, these are the same thing. All right, we're going to move forward. So next up, we have properties of a base. These are also called alkalis. So they're also called alkalis. Bases, they taste bitter and they feel slippery. So whenever you think about a base, think about soap. So bases, they also form electrolytes, which means when we put something like NaOH in water, what's going to happen is it's going to dissociate to form Na plus and OH minus. So it forms ions when we put it in water, and because it forms ions, it will conduct electricity. Bases have a pH that's greater than 7. So anything greater than 7 would be considered a base. 7.1, 8, 9, 10, all the way to 14. These are all going to be bases. So what's the difference between caustic and corrosive? You don't have to worry about this, but caustic, that's a chemical fire. It's a chemical burn. If you get a base on your hand, it's going to burn your skin, but not in the burn that you're used to. Not a fire burn. It's going to be a chemical burn. It hurts your skin. Very painful. Yes. Except bleach is rarely as concentrated as the bases that we work with. Yes. So that means when you put it in water, it stops being NaOH. It becomes Na and OH. So when we put NaOH in water, so NaOH plus H2O, I'm putting a formula up there. When you put it in water, it's going to form H2O, but it's also going to form Na plus and OH minus. Yes, they both dissociate and they're both electrolytes. All right, let's move on. All right, next we're going to talk about the Arrhenius definition of an acid. We did this last week, but we're just going to go over it again. So Arrhenius's definition of an acid is anything that when you put it in water, it produces an H plus in the solution. So it has to have hydrogen in the formula in order to be an acid. H plus is known as hydrogen ion, and it's also called, very often, it's also called a proton. Because it's just a proton, there's no negative charge to it. And they're typically depicted as hydronium ions, which are H3O+. So acids are going to be H plus and H3O+. All right, Arrhenius's definition of a base is going to be anything that forms hydroxide in a solution. So OH, that's known as hydroxide. So anything that has a hydroxide in it would be considered an Arrhenius base. This isn't the definition that we currently use for acids and bases. We're about to get into Bronsted-Lowry, but you need to know the difference between the Arrhenius definitions and the Bronsted-Lowry definitions. If it has hydroxide and it forms hydroxide in solution, then it's a base. All right, let's move on. All right, next we have the Bronsted-Lowry definition. So in Arrhenius's definition, an acid is anything that has hydrogen in it and gives away hydrogen. A base is anything that has hydroxide in it and gives away hydroxides. Now, in Bronsted-Lowry, an acid is any substance that can donate a hydrogen ion. So an acid is anything that gives away an H+. An acid is anything that can give away an H+, which is very similar to Arrhenius's definition of an acid. It doesn't change until you talk about bases. So a base is any substance that can accept a hydrogen ion. So a base, it can accept a hydrogen ion. An acid gives hydrogen away. A base accepts hydrogen. And just know that we also refer to the hydrogen ion as just a proton. So acids are proton donors and bases are proton acceptors. The difference in the base definition is Arrhenius said that bases have to have hydroxide. Bronsted and Lowry said they don't have to have hydroxide. They just need to be able to accept the hydrogen. All right, and then conjugate pairs. We also talked about these last week. So a conjugate pair, that's what's left over when the after the reaction occurs. We'll talk about them a little more on the next slide. All right, let's move on. So here's our simplest definition. Acids are going to be proton donors. Bases are proton acceptors. And the proton we're talking about is going to be H+. So let's go ahead and move on. All right, so the acid on one side reacts to become the base on the other side. That's what we're talking about when we're saying conjugate pairs. So let's just get straight into solving it. So here we have hydrochloric, so HCl. Is this going to be an acid or a base? What do y'all think?
I think it's an acid.
All right, so it is an acid, but an easier way of figuring out if it's an acid or base is look at it and then see what it becomes on the other side. So HCl becomes Cl minus, which means what did HCl do? So is it an acid or a base? It's an acid. Now we can look at H2O. What did H2O do? So acid or base? Base. Now, the other side, this is where the conjugates go. The conjugates are going to be what you're left with. So, and to better explain what conjugates are, I'm going to write this reaction in reverse. So I'm going to do H3O plus Cl minus, and then I'm going to do the arrows. Don't write this, I just want to show it to you. And then HCl over here plus H2O. So all I did was I rewrote this reaction in reverse. If I write the reaction in reverse, what is H3O plus? Is it an acid or a base? What about Cl? This would be the base. So now I want to show you the conjugates. So HCl becomes Cl minus. But down here, did Cl act as an acid or a base? So here we're going to call it a conjugate base, which means in the reverse reaction, it's not going to act like an acid. It's going to act like a base. What about H3O plus? In the reverse reaction, did it act as an acid or a base? So here we're going to call it our conjugate acid. So the base always forms the conjugate acid, and then the acid always forms the conjugate base. And what that means is if you reverse the reaction, it's going to act like this other thing. So I'm going to go ahead and clear this page, and I want you guys to write the next one, and I want you to answer it. So acid, base, conjugate base. All right, so let's take a look at this one. So NH3 becomes NH4. Did it accept or did it give up a hydrogen? So acid or base? All right, H2O, did it lose or gain a hydrogen? Acid or base? Acid. So now NH3 on this side, what is it? What is it? A conjugate acid or conjugate base? This is our conjugate acid. What about hydroxide? This is our conjugate base. All right, so here we have some practice. Write the conjugate base for the following acids. You're going to see this in the assignment that we're going to work out very soon. But to do this, it's very simple. All you're doing for the conjugate base is you're going to write what it looks like when it loses a single hydrogen. So sometimes that's easy. Most of the times it's easy because most acids start with hydrogen. Here's one of our exceptions of an acid that doesn't start with hydrogen. But just a heads up, you're going to lose a hydrogen here. You're not going to lose a hydrogen from the CH3.
Is it CH3 because the compound?
They're both polyatomic ions. But let's take a look at A. So it's going to donate a hydrogen. So what's it going to become? What is it? It's going to be ClO4 minus. Make sure to also include the charge. So I'm going to give you all 1 minute to solve the rest of these. All right, so let's go over these real quick. So the first one, what's it going to become? H2PO4 minus. What's the next one? CH3NH2. And it loses the charge. What does CN become? HCN. What about H2O? H3O plus. Easy, right?
Yes, sir.
All right, let's move on. All right, here's our next one. Here we're just going to... Actually, we don't need to do this. You're going to see this on your assignment, so we're just going to move on. Next up, we have neutralization. This is just a definition of a type of reaction that occurs. So go ahead and write neutralization. So neutralization is exactly what it sounds like. This is a chemical reaction between an acid and a base, and it always leads to something that's more neutral than what you put in. So whatever you end up with is going to be less acidic than your initial acid. It's going to be less basic than your initial base. The products of a neutralization reaction are always going to be a salt and water. So anytime you add an acid and a base together, you're always going to produce water, and you're always going to produce some type of salt. And by salt, I mean ionic compound.
So, can you technically drink it?
You can't drink every salt. Some salts are will kill you.
Oh. I don't think that's good.
Can you eat basil?
No, you can't. That's an example of a salt that will kill you.
Which one?
Basil.
Which one?
Basil? Like Epsom salt and stuff like Well, I think you can eat Epsom. You can't.
You can't eat Epsom salt.
But like people do the thing where they wish it in their mouth. If they have like, what's it called?
They're probably better salts than Epsom salt.
Yeah.
All right, let's go ahead and move on. So what are the products of a neutralization reaction? Salt and water. All right, let's move on. We're about to get into the math, the mathematica. All right, so here's our pH scale again. You don't need to write all this down because most of this you already know. What you don't know, you definitely want to write down. So first of all, what does pH stand for?
Power of hydrogen.
Power of hydrogen. So each change on the pH scale is to the power of 10. What does that mean? How much more acidic is a 7 than an 8?
10.
It's 10 times more acidic. So anytime you go, you change one number, you're increasing tenfold, so 10x. So 7 to 8, 7 is 10 times more acidic than 8. You already know that 0 to 7 is an acid. You don't need to write this. 7 is neutral. And then 7 to 14, that's going to be your bases. All right, let's keep going. All right, so here we have another image. So this one is very, very important. It's a very valuable picture because it shows you a lot of real important information. But I'm going to show you this same information on the FET simulation that we used last week. So here we have a neutral solution. Oh, let me reset it. Here we have a neutral solution. So this is just pure water. All it's got is, it's got H3O plus, it's got OH minus, but it's got the same quantity of each. 1.0 times 10 to the minus 7, 1.0 times 10 to the minus 7. If I click here, it's going to show me a particle count where they're exactly the same quantities of both. Now, what's going to happen if I increase the H3O quantity? What happens to the OH quantity? So as this one increases, you know the other one decreases. So I'm going to remove the particle count. And what I want y'all to see is when they were neutral, you have the same number of both. But as we increase one, you're decreasing the quantity of the other. So that means if you have, so this right here, this is a very powerful base. 1 times 10 to the power of 1, this is a very, very strong base. But does that mean it doesn't have any hydroxide in it?
No.
No, we still have hydroxide. There's a few of them right here. There's very few of them in comparison, but you can't assume that there are no hydroxides. If we decrease the quantity of hydroxide, you can see that we increase the amount. Sorry, if we decrease the amount of H3O plus, we're increasing the amount of OH minus. And that's just something that I want you all to see, this ratio that we got. Now, coming back here, if something has a pH of 0, 1 second. Well, if something has a pH of 0, that means it's got a lot of hydroxide ions. So I'm going to erase this. I want y'all to see. So here we have 1 times 10 to the power of 0, and here we have 1 times 10 to the power of negative 14. Which one's a bigger number? 1 times 10 to the power of 0. What is 1 times 10 to the power of 0? So this is 1. But it's much larger than this number, which is 1 with 13 zeros before it. So it's a much smaller number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 1 is a much larger number than this number up here. And as we decrease the amount of H plus, we're increasing the amount of OH until we reach the 7 where we have equal quantity of both. So at 7, you have the same amount of hydroxide as you do H plus, and then that's where you have a neutral solution. So this image, I find it pretty helpful in understanding this stuff, but we're going to go ahead and move on from here. There's nothing you need to write from this page. All right, so next up, we already talked about this. So orange juice has a pH of 3. That's 10 times as much H plus as tomato juice, which has a pH of 4. And we're going to do math related to this stuff in a little bit. All right, next definition I want y'all to write is an indicator. So an indicator is anything that, so it's a chemical that changes in color based on the presence of H plus and OH minus. So the indicator that we're using here in the front is phenolphthalein, which is not one that's listed here, but it's a clear liquid that churns green in water, and then it's clear in water, and then it churns red in base. But there's a lot of different indicators that we can use. A bunch of them produce different colors, but that's what you need to know about an indicator. An indicator is something that changes color based on the pH. In a minute. I wouldn't leave right now. All right, we're going to move on. So an indicator is a chemical that changes color in the presence of an acid or a base. All right, let's get into the math. All right, so we're almost at the math. We're very close. So next up, we have our definitions of strong acid. So what is a strong acid? It's a strong acid is one that fully dissociates. What does that mean? But what does fully dissociates mean? So fully dissociates means that all the acid or base are going to break apart in water. You're not going to have any of the original acid or base in that water. So you're not going to find any HCl in the water, because all the HCl turned into H plus and Cl minus.
So does it just become water?
It becomes water with, look here. So it becomes water with H3O plus and Cl minus. You don't have any HCl left in the solution. There's none of this. All right, let's move on. So next up, we have weak acid. A weak acid is one that only partially dissociates into ions, which means most of it stays as it is. So take a look at this little picture I got here. So here we have an ion. Here we have an ion. But then there's also places where we have the full. So right here, we have, it's not an ion. This is the weak acid. Here we have a weak acid. Here we have a weak acid. Here we have a weak acid. So it does form some ions, but it also leaves the acid in the solution. Most of the acetic acid molecules do not dissociate. And on the next slide, I got a picture that's going to be very helpful. All right, so this picture is a little bit nicer. So over here, we have a strong acid. A strong acid, when you put it in water, it's going to form, let's say that this is 1 mole. When we put it in water, it's going to produce 1 mole of H plus, and it's going to produce 1 mole of the spectator ion. So if this was HCl, we're going to have 1 mole of H plus, and we're going to have 1 mole of Cl minus, because that's what strong acids do. They fully dissociate in water. Now weak acids, take a look at the weak acid. The weak acid, like hydrofluoric acid, HF is a weak acid. If we have 1 mole of it here, over here we're going to have 0.9 moles. And then here we're going to have 0.1 mole of H plus. And then we're going to have 0.1 moles of our spectator ion, which is F minus. Why not? So if you have 0.1 moles of H plus and 0.1 moles of F minus, you're going to produce 0.1 moles of HF. So look here. Here we have 1 mole of a strong acid. And then when it dissociates, you produce 1 mole of H plus and 1 mole of Cl minus. Over here, if we have 1 mole of hydrofluoric acid, only 10% of it will dissociate. So 0.9 is going to stay its original form of HF. And then 0.1 becomes H plus, and 0.1 becomes F minus. Only 10% will dissociate. Stays the same. All right, so let's come back here for a second. There are 6 strong acids, and there are 6 strong bases. When you get to college, you're going to have to memorize these. Some high school teachers and AP, definitely AP, they make you memorize these. But these are the 6 strong acids. Any acid that's not a strong acid is what? It's a weak acid. So there are only 6 strong acids that we talk about, only 6 strong bases that we talk about. The bases are really easy to remember. Let me show them to you real quick. So the bases over here, look over here. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. These are the 6 strong bases. They're right here.
Are we just like in a line?
You call a line.
1, 2, 3, and then short break. We can make it.
The strong acids, they're a little bit more difficult. So we do have HCl, we do have HBr, we do have HI, but then you also have nitric acid, sulfuric acid, and perchloric acid, which all have polyatomic ions in them. These are the ones that students mostly forget. So that's one the students forget, that's one students forget, and that's one students forget. But if I were you, I would write these all down. You don't need to write their names. I would just write their formulas. Strong acids and strong bases, I would write them down. That way you know if it's not one of these, it's got to be a weak acid.
So just write down
All right, so y'all remember electrolytes? Are acids and bases electrolytes? Yes, they are. So a weak acid, do you think it's going to be a weak electrolyte or a strong electrolyte? So weak acids go here. What about weak bases? Are they going to be weak electrolytes or strong electrolytes? All right, so the weak bases also go here. Now, strong electrolytes, what are they going to be? Strong acids and strong bases. I would just write down somewhere weak acids and bases are weak electrolytes. Strong acids and bases are strong electrolytes. All right, let's move on. So strong acids are what type of electrolytes?
Strong electrolyte.
Weak acids are what?
Weak.
Strong bases are what?
Strong electrolyte.
Weak bases are what? All right, so strong acids conduct or do not conduct electricity? Weak acids? Strong bases? Weak bases? All right, good. We're not going to review this. Or do y'all want to? So taste bitter is what?
Base.
pH less than 7.
Acid.
Sour.
Acid.
Produces hydronium.
Base.
base
Are you sure?
HF.
Acid.
What is hydronium?
Acid. No? It's an acid.
All right, it's an acid. So hydronium is H3O plus, so acid. Feels slippery.
Base.
Produces hydroxide. Low hydronium ion concentration. Low hydronium. Low hydronium is going to be a base. Dissociates in water. That's going to be acids and bases. Known as alkali. Greater than 7 the pH.
Base.
Neutral.
Oh.
H2O.
Agua.
All right, we just made it to the math. All right, let's start the math before Dario gets here.
What happened?
Do you know which water bottle is whose?
Yeah, this is the label.
All right, let's go ahead and work through this. All right, so the strength of an acid is based on the H3O plus concentration, but these values are often very small numbers. That's why we express them in logarithms. So I'm going to start off by giving you the formulas, and then we're going to start working these problems out. So these are 3 of the formulas that we're going to use today. There's 2 more, but let's start with these 3. So to calculate the pH, pH is equal to the negative log of your H plus concentration. To calculate pOH, you're going to need the negative log of your OH concentration. And then the last one is that your pH plus your pOH needs to equal what?
14.
Will always equal 14. So if you have your pH, you can calculate your pOH by using this third equation.
So we have a pH of 7, the pOH 7. Boom.
All right, let's keep moving. I would go the other way. All right, so let's go ahead and work these out. Everybody grab a calculator. All right, so it says, what is the pH of a solution where your H plus concentration is 1.0 times 10 to the minus 9? So first, let me start by saying this is really, really easy math. But if I lose you right now, you're going to be lost for a long time. So please, everybody grab your calculator. Let's do this together. So what is the pH of a solution where your H plus concentration is 1.0 times 10 to the minus 9? So first thing you're going to do, you're going to turn on your calculator, and you're going to push the negative button. Clear it first, and then push the negative button, and then push the log button.
Where's the negative button?
The negative button is the one under the 3. So press negative log, and then you're going to put in 1.0 times 10 to the minus 9. Log is right next to the 7.
Oh, I see it. What is it to the power?
So this right here, your H plus concentration. All right, so what's our answer for this one? All right, so for this one, our pH is 9. All right, so next question is on the same page. So our pH here is 9. The next question says, what is your pOH? So our pH is 9. Our pOH needs to be 14 minus 9. So 14 minus 9 is 5, which means our pOH is equal to 5. Easy, right?
Yes.
All right, let's move on.
Wait, can I write that down? Wait, hold on, go back, please.
All right, so the next one says, what is the pH of a solution with an OH concentration of 1.0 times 10 to the minus 6? So let's go back. I'm going to write the formula for pH. Could someone read it to me? pH is equal to what?
Negative log H plus.
Negative log of your H plus concentration. Do we have our H plus concentration?
No.
What do we have?
We have OH.
So what can we calculate with our OH?
The power of OH.
So pOH. So to calculate pOH, what's our formula?
Negative log, then use the OH.
Negative log of our OH concentration, which is 1 times 10 to the power of minus 6. So plug this into your calculator. All right, so our pOH is equal to what?
6.
Our pOH is equal to 6. Now to calculate our pH, what do we got to do?
Use the Pythagorean theorem.
Nope,
It is kind of perfect.
it's not. So
14 minus 6.
it's going to be 14 minus 6. So what's our pH?
8.
Shh. Our pH is what?
8.
So is this an acid or a base?
Oh, it's what's it called? Acid.
So our pH is equal to 8. So is this an acid or a base?
Oh, it's a base. My fault.
This is a base. All right, so I'm gonna go ahead and give you the let's do 1 minute to solve the next one.
It's just like is 8 times 10 to the minus 10. Yeah, right. Go back. It's I'm gonna say 9.1.
All right, so what did we get for the OH concentration?
9.09, but I'm gonna round it up to like 9.1.
All right, so our POH is equal to 9.1. So then to get our pH, we're just going to do 14 minus 9.1. And what does that give us? 4.9 for our pH. So is this an acid or a base? This is going to be an acid. All right, so let's move on. So the next thing, this is going to be calculating H plus from the pH. This is just as easy. It's not difficult at all. You're just going to do the inverse log key. All you're going to do is you're going to press second and log on your calculator. It's going to give you 10 to the power of. And then you got to plug in a negative pH or POH. So let's do this one together. So if we have a pH of 7, what we're going to do in our calculators, everybody turn on your calculator, press second log. It should give you 10 to the power of. And then you're going to do minus 7. So 10 to the power of minus 7. Second is the button at the top left corner. All right, so let's do this again. Press second, log, and then negative 7. Did you push minus 7? All right, you're going to do negative 7. Negative is the number under the 3, or the dash under the 3. So you should have got 1e negative 7. What is 1e negative 7?
1 to the power of 10. Wait. 1 times 10 to the power of negative 7.
1 times 10 to the power of minus 7. All right, let's go ahead and do this next one. The next one says, the next one gives us our OH concentration. What can we calculate using our OH concentration? We can calculate POH. So let's do that one first. Which formula do we use? Negative log of 5 times 10 to the power of negative 5. What do you get for that?
4.3.
All right, so our POH is equal to 4.3. What's the next thing we can solve for? So we're going to do, what do we plug in to get that? 14 what? Minus 4.3. What does that leave us with? 9.7. And what is that? This is our pH. And then is this solution acidic or basic? All right, so this is going to be a base. All right, so this right here is what your actual assignment's going to look like today. I don't want to spend too much time on this one, so we're going to go through the first couple together, and then I'm going to let you do C and D by yourself. So let's take a look at A. A gives us our H plus concentration. What can we use that to solve for? We can use our H plus to solve for our pH. So let's do that first. Everybody, negative log of 5.4 times 10 to the power of minus 4. So what's our pH?
3.3.
Our pH is 3.3. So now that we have our pH, what can we solve for next?
If one is acidic and 10.7.
What can we solve for? We can solve for POH. So what do we do in our calculator? 14 minus 3.3. So what's our POH? 10.7. And then our last step is we need to calculate for our OH. What do we do here?
10 inverse log.
10 to the power of
Negative 7. Negative 10.7.
minus 10.7, close parentheses, and that should give you your H plus or OH concentration.
Second log. Even if you round up, it still gives you 2.
All right, so in your calculator, you should have put in, you should have hit second log. That would have given you 10 to the power of, and then you put, yeah.
It's a long number.
Well, our answer should only have two significant figures.
Except even if you round it up, it's gonna give you 2.
We're just gonna call this 1.9, or no, we'll call it 1.9. No, we'll call it 2. We'll go 2.0 times 10 to the power of negative 11. Now, is this an acid or a base? It's an acid. What do we use to determine that? pH or pOH? We always use the pH. So let's get the next one. The next one gives us our OH concentration. What can we use that to solve? We can use that to solve pOH. How do we do that? What do we plug in? Negative log of 7.8 times 10 to the power of negative 10. What's our pOH? 9.1. Now what can we solve for? How do we do that? What does that leave us with? 4.9 goes here. And then how do we solve for H plus? So second log, negative 4.9. And then what does that give us?
1.3 times 10 to the power negative 5.
And then is this an acid or a base? Acid. All right, so I'm going to give you guys a couple of minutes. You don't need a couple, but I'm going to give you a couple to solve C and D. While you guys do that, I'm going to be handing out today's assignment. All right, so let's go ahead and finish off the rest of this. So for C, they give us our pH, and we can use that to calculate our pOH. So we're just going to do 14 minus 10.75. Shh. That's going to leave us with 3.25. And then we can use both of these to calculate our H plus and OH concentration. So we're going to do 10 to the power of, on your calculator, that's going to be second log, 10 to the power of minus 10.75. And that should give you 1.77 or 1.8 times 10 to the power of minus 11. And then for the other one, we're going to do second log and then minus 3.25. And that's going to give us 5.6 times 10 to the power of minus 4. And then because of our pH is so high, this is going to be our base. Now this last one, let's go ahead and solve it the same way. So we're going to do 14 minus 5, which leaves us with 9 for our pH. And then our H plus concentration, we're going to hit second log, minus 9. That gives us 1 times 10 to the power of minus 9. And then over here, it's going to be the same thing, except 1 times 10 to the power of minus 5. And because our pH is 9, this is also a base. So that's it. Go ahead and work on your worksheet. I'll see you guys next time.